Okay. Up. Laser pointer active yet. Sometimes when we look at galaxies, like obviously this elliptical stuff here, which is the Galaxy NGC 4261. And then basically Hubble Space Telescope. And on the left side, what you see is ground-based optical. I don't know which observatory took. And radio image. The entire picture, the width, as you see here, is 88,000 light years across. It shows this galaxy, obviously some elliptical stuff. And very likely from the radio image, we get these jets. We see that there are jets coming out. So we would call this an active galaxy. Oh, this would be clearly a radio galaxy. But we see there's also other radiation occasionally coming out. And this leads us to the objects that are called QUASARS, quasi-stellar objects. So if we take then the Hubble Space Telescope and zoom in to the, you see here, this here is a length of only 400 light years across. Well, there's a very bright spot and a ring around that sounds okay, or torus rather than a ring. That sounds again like something is or gas is compressed, heated up, accelerated towards something, but of course angular momentum barrier, it cannot directly fall in, it needs to spiral around, we get magnetic fields, we get particles that are trapped in this field line gyrate along. What gyration means it basically, if this is one finger is the field line, then the particle is going around, and it again travels along this field line until the kinetic energy says no, or if it travels into a region with a higher field line density, it loses energy, it gets stopped, and then it gets accelerated back again. What means we have no accelerated charges, they emit radiation, Bremsstrahlung. So, and some galaxies emit these jets of particles and radiation. And the jets seem to originate from the center. So this is then called an active galactic nucleus. Okay, what will be the center? We had this already a couple of times. It will be a supermassive black hole. So a couple of million solar masses black hole, and everything that comes nearby into this massive gravity is of course massively accelerated. If we have gas cloud, it gets accelerated, it gets hot, because now the maximum Boltzmann distribution is shifting towards more the high energy or high velocity part. It's hot, collisions can ionize basically the atoms. The electrons get detached from the atom. Therefore, we have ions and electrons, we have charged particles, they are moving, we get exactly, we get magnetic fields. But we have basically, so this is accretion disk, or the accretion disk is directly around, but obviously there's also this torus of hot gas. So the same mechanism as we always had. Often this stuff is in the radio. Why is it in the radio? Well, it's a violent event. We would expect it to be X-rays, gamma rays. This is when it happens nearby. But if it happened very far away, what happened with this light? Of course, it needed to travel and the space expanded. That means we get this expansion redshift that is associated with the expansion of space with time. So we get no longer X-rays, a hard radiation, it's shifted all the way down to the radio waves. Why is this nice and comfortable? We can do radio astronomy nicely Earth-based, so we don't need to pay an expensive satellite. We can buy us, or we can build us an expensive big radio telescope. Or then what we get out, if we split this light into its spectral distribution, well, here's obviously one spectral line, and the rest. This is what we would call Bremsstrahlung. So again, we have typically this coming out from, this is from Centaurus A, so not too far away. What means here, this is not subject to this redshift, and we get the hard radiation. Of course, then we need again a satellite to record this stuff. Typical Bremsstrahlung spectrum, what is an indication that here accelerated, deaccelerated charges are making this radiation. So we have this dynamo mechanism at work. There's the gas flowing in the accretion disk, creating these magnetic fields, or plasma creating the magnetic fields. Particles that are trapped in this magnetic field are accelerated, deaccelerated, produce radiation. The acceleration is so big that often we can basically conclude there must be a supermassive black hole associated. In fact, all bigger galaxies, we can assume, have this supermassive black hole in the center. So, and if such a radio galaxy, if it's radio, means it's very far away. How will this appear to us? Will we see the extension of the radio waves of the galaxy? No. This is so far away. All we see, there is something, so some dot. So this appears to us as it would be a star. And if we didn't know about massive or the redshift so much, we would assume this is a quasi-star, and therefore QUASI-Stellar Radio object, QUASAR. Well, sometimes the Earth is directly in this. Sometimes we have seen nowadays basically this jet going out perpendicular, and we could nicely look at it from the side. But sometimes we are directly or very close, at least, to this observation, or with our axis observation almost coincides or even coincides with the jet. Well, then we would call this object a BLAZAR, blazing quasi-stellar object. What we get, BLAZARs, this is really the hard radiation. If we look from the side, what we get is rather the radio, so the soft radiation. So a radio loud is range if we are directly in the line of sight, and then if we are almost perpendicular, then we see a radio galaxy. Oh. So these are active galaxies, and so they are far away, the pure point line, what means they must have been subject to a massive redshift. And this is now, if we take one of the spectra of this QUASAR KUV 18217 plus 6419, whatever this means, I think this here are coordinates somewhere. This has a redshift of 0.297. Now we could go back to our map that we have seen at the very beginning and look how far is this away. Where do we get this redshift from? Well, you clearly have the hydrogen lines, so alpha, beta, gamma. There would be somewhere delta expected. And from there, this is where we would expect them in the lab. These lines, this is where we observe them. So this is clearly where we immediately can extract the redshift. So they are very far away usually. That means they are old. They are a relatively young galaxy. This means there was loads of stuff around that the massive black hole in the center could feast upon and grow. So if they are active, they are often very luminous, but the light output can exceed often the entire galaxy. So, and obviously, what is here the case? We see that the jets are not going perpendicular to the plane. So obviously, there must be something twisted towards. This means also this can change the direction where they emit the jets. And it's not continuous. So if you have 4 times 10 to the 14 solar luminosities, 400 billion times as bright as the sun. But at the redshift, so this one here, found that redshift of 7.54. This means it was very, very early. If you remember, this must be this roughly less than 1 billion years after the Big Bang, so 12.8 billion years before. Okay, here it's written 700 billion. And here the mass of the central black hole, that would be 800 billion solar masses. So very violent stuff, yet not continuous. So if we look at these quasars we see 279 over the time, so basically take all the photo plates for 20 years or the radio observation for 20 years and plot the magnitude. This is again a logarithmic scale. What you see here is the power. Then we see occasionally there are eruptions. Then it's a bit quieter. It's no regularity. There is not really something going on continuously. Oh, there is continuously going on, but not in a nice sinusoidal or regular fashion. That means the black hole is fed from time to time, but not regularly. Well, then, so might be nice to have an impression how this looks like, what you see here. By the way, we have seen this a couple of years ago in a neighboring galaxy. Basically how it started really to shine up, and then it was relatively focused. So one could observe the X-ray emission from a galaxy where the central black hole was just eating a star. And how this looks like, an impression you can get here in this video. Where you see the star comes too close to the central black hole, get spaghettification, so it gets ripped apart, it gets sucked around to do basically this the accretion disk, and then you see also the jets coming out, and the stuff is until it's all eaten. Oh. So all larger known galaxies have such a supermassive black hole in the center. can easily exceed 1 million solar mass, and you have seen this supermassive one with this 400 solar masses. In fact, they are sometimes really challenging, these ones at a very early time of the universe, because there is also a maximum amount that the black hole can feast at a given time. So the feasting rate is also limited, and then when they are too big, how could this happen? So there seems to be quite some challenges for theory by this observation of these very early quasars or supermassive black holes that appear for us now as quasars. So it's of course a question, where do these supermassive black holes come from? Well, there is now essentially two possibilities. Of course, we had at the very beginning this accumulation of dark matter, which then led to the formation of bigger structure. And then in the very beginning, this gas cloud, after the Big Bang, there might have been regions so dense, big and dense, that the gas basically was so much that the star would have exceeded 130 solar masses, and then would get a direct collapse to a black hole. This is one chance, and the other chance is, of course, at the very beginning, that we had these massive, super big stars. The super rock stars, so basically they burned for a couple of million years, if at all. Then make boom. Then leave behind the black hole, and this starts feasting. And there's of course loads of material around, so it quickly feasts and grows. But there seems to be this limit on how much a black hole can eat at a given time. Therefore, the growth rate is of course then limited. Yet, so of course then the question, what was there first? The supermassive black hole or the galaxy? Did galaxies evolve around supermassive black hole, or could these black holes then become so big because they had this galaxy around? What was their chicken or the egg? Or something to look forward, that maybe James Webb will give us the answer, but maybe not. Okay, so let's come home. So we have now basically galaxies in general, and now let's come to the ones that most matters to us, our own one. According to this picture, it's a nice barred spiral. So we have these two main arms, and then there seem to be a couple of side arms in between. It's of course a question, who has taken this picture? Did we send somebody to outside of our Milky Way? If this here is 100 light years across, must have been quite a distance away, or did we somebody ask the guys in the Andromeda galaxy to send us a picture? Yeah, this is of course just an artist impression. But an artist, in order to paint it and that it's accepted and often used, so we need to obtain somehow this knowledge that we live in this barred spiral. How can we gain this? Well, first of all, we look at the night sky. And if it's dark enough around us, then what we will see is this band of the Milky Way. So this band of stars that goes basically once over this night sky. And it doesn't matter where we are on the planet. because it's going to stay a band. Then the density of stars is decreasing, going basically away from this band. This tells us we live in a flat in a flat galaxy. Well, stars are still out of the plane, above and below, so it must have also some vertical extension. And if we go to the south, so the hemisphere, we observe there's a part of this band which is much more bright. So it must have also a center. We are not in the center. Oh. So another marker that we can use is if we assume these globular clusters. These satellite galaxies that here, this M80, we nicely see this is basically some spherical symmetric stuff. You see is 30,000 light years from the sun and several hundred thousands of stars. Globular clusters. Globulus is, by the way, the Latin word for small sphere. They orbit usually larger galaxies. Milky Way, we know of 158, perhaps by now we know of more. This is now 3 years old. Andromeda seems to have around 500 of them. And M87, a large elliptical galaxy, but obviously not too far away and could be observed by Messier. So before the end of the 18th century or 17th century. Yeah. No, 18th century, sorry. This has more than 13,000 of these globular clusters. Whew. Well, how are they made? Very likely when there was the galaxy was cannibalizing another galaxy, and then there was a bit of an overshoot, and the stars then again started with clustering together. Basically, like when you take a chunk of water and you spill something on the ground, you will also find the individual drops. Well, the good thing is they contain C-fate variables. That means we can now obtain the brightness of them, we get the distance of this globular cluster. Well, we do so for all globular clusters, and we assume they are equally distributed around over the plane of the galaxy and below the plane of the galaxy. And then we get our relative position in the galaxy. So we assume they are basically equally distributed, and now we can check how many of them are behind us, how many are in this direction, how many are in this direction, more west, north, and how much do we see there. Of course, on this side, we have a problem because the center of the galaxy is so bright. Obviously, we cannot look behind. Okay. What means we can now get our relative position of the sun to the center of the galaxy. Turns out we are this 28,000 light years or 30,000 light years away from the center of the galaxy. That means already towards the outskirts. We live in galactic suburbia. Of course, we have to be careful with if you apply such methods that are based on the brightness. Some dust in the galaxy, especially, of course, a galaxy, you have the problem that there you have more dust and regions occasionally with even more dust, and then the brightness of the stars might be obscured, and therefore the distance falsified, that we put them too far away. Or every method has its drawbacks. Of course, then we know already roughly where we are. We know it's a flat band. We see the the southern hemisphere, this accumulation that's brighter, that looks a bit more like a bulb or a longer rugby ball a bit, which is the center of the galaxy. But then we can again start having the entire view of our observatories. They are expensive enough, so let's use them. And map once around the galaxy around us. We do so, radio continuum, what do we see? Well, it's of course normalized to this Sagittarius A, where the center of the galaxy is. And this is the plane in the galaxy. If you go to the dark place, you could adjust this a bit, and very likely what we see is this kind of stuff, and then coming here again. So radio continuum, we see there is something going on in the center, and here seems to be something, and there, and here a bit more. And we can use atomic hydrogen, 21 centimeter line, or this Balmer series line, if you do it in the optical, we get the hydrogen distribution. And I wonder that there were so few in the center. So obviously our galaxy might also blast out in the center. We look for molecular transition of the another radio continuum with longer wavelengths, or again similar like here. These two bulbs. Molecular hydrogen, here we have a lot, here we have a lot. And near the center seems to be the stuff more molecular, what I wonder about, because molecular I would assume is less temperature than atomic. Somehow the bond is not so super strong. Infrared, similar picture. Out here a bit again, center bar, and another mid-infrared, near-infrared, optical, and then we see that we often don't see anything of the center. There is obviously something very bright, but lots of dust clouds, which block our view. Well, X-ray, there seems to be again something going on. Something is here below. And I wonder that it's not so much. Of course, the gamma ray, we clearly see there's something active in the galaxies. And again, this right and left. And more out here, we constantly see something. Oh, so there seems to be rings. This is what we can conclude from here. And well, we are clearly also seeing one direction is brighter. This means we cannot be in the center. In fact, here we could now again look, this is the center, and then where's the mass distribution in terms of this kind of stuff. If we are in a homogeneous disk, that would be, of course, immediately tell us how far we are out. But this is not the case. In the center, it's of course denser. Well, the center is again southern hemisphere. We see all this dust, and then we see it here so bright because there are so many stars. Well, there's this Isaac Asimov, this the grandmaster of American science fiction. He has this foundation cycle about the galactic empire. At the center of this galactic empire is then nearby the center of the galaxy. And there he mentions in one sentence that the night sky is, of course, very bright. Of course, when you're in the center and you have so many stars around you, you have so many light sources that it appears much more rich in stars than for us on the outskirts. But by the way, when it comes down to really good science fiction, then I would recommend you Stanislav Lem. His short stories are usually very humorous and interesting. He's a very educated man. He was a medical doctor, but his understanding of physics is amazing. And he has a very, very rich imagination. And his stories are really, really good. At the moment, maybe a bit cynical, what is called Fiasco. So if you want to read very good science fiction, now soon is the summer break coming after the last round of exams, that you might have time, Fiasco by Stanislav Lem. But all the other books, the Star Diaries and so on, are excellent. So from science fiction, then, of course, usually I would now also say recommend Russian literature, but War and Peace is obviously not so nice at the moment. But we might understand, reading War and Peace would understand why the Russians are so paranoid. Okay, so we have obviously here a center which is quite extended. It's not radial symmetric. We see that it's relatively extended. So it's rather bar than a spherical distribution, a bulk. But obviously also loads of dust that obscures it a bit. Well, and again, we could take this atomic height on. Well, so we have the center, but how do we know about the other structures surrounding us, that we are really in this in a disk with spiral arms? Obviously here, this is a strong indication that there are some spiral arms. Here is a bit the same, but of course less intense, therefore we would expect less matter or less sources of radiation, or colder simply. Well, and now what helps us a lot is again this 21 centimeter line. First of all, it's Earth-based radio telescopes, always good, or Earth-based telescopes, always good. We can build them much easier. Okay. So we use this 21 centimeter line, which was originated that the electron rotates the same way as the nucleus does, and now it basically starts going the other way around. So from clockwise to counterclockwise, what means we would now indicate this rotation by this arrow of the where the rotational axis points to. For the physicists, you're going to learn that all these intrinsic rotations we call spin. But they are later on, we just represent them by up or down, by an arrow going up or going down. So this characteristic wave. And now, since we know the wavelengths that should come to us, we can look, is it Doppler shifted? So if we look from here and through the inner rings, so this would be the galactic center, this GC. If we look here and the stuff is rotating relatively to us, then we get here only a small fraction of this velocity is going towards the line of sight. Here, obviously, a larger fraction. So this would appear to be faster. And now comes this Doppler shift into account when the source of radiation is, or of the wave is moving relative to us, that we consider ourselves to be at rest. If it comes towards us, the wavelengths will be shorter, and if it moves away, the wavelengths will be longer, or the frequency gets higher, the frequency gets lower. And from this, we can directly match the velocities out. So C, this would be going up here. And obviously, it has here just the same shift. It doesn't matter where the projection comes from, left or right of the line of sight, as long as the projection order is the same. So we get now directly the information, how much of this hydrogen that we see along this line of sight, where is it placed? So D, this is obviously almost moving almost perpendicular if there is no Doppler shift. Oh. So, and from this, the galaxy or Milky Way rotates once about every 225 million years. This means since about the dinosaurs came to existence, our sun basically once walked around the Milky Way. Or since life jumped from sea to land. About 700 million years ago, 3 times, if we use this as a clock. So, give you a feeling. Or our sun speeds to the galaxy with about 240 kilometers per second. Oh. So quite something. Now we can use basically this 21 centimeter line and make a galactic map. And we see the galactic center. We see the shadow because they're so bright, we can't see behind. And then we see this map. So we are here. Again, galactic center. And then we would assume, or from this data, we get basically this, that it must have this bar, and then the different spiral arms coming out. And now you see that we have basically more that origins somewhere here in the center, but I think it's a few major ones. Then you see here new outer arm. So this is basically the structure of our Milky Way. And what we would think it looks like if we could fly outside and take a look at top. Okay, now, of course, the center. If you remember, I have shown you this film already, which have been won the Nobel Prize, I think 2 years ago. And was the European Southern Observatory, so the Chile, there, I think it was not only the Very Large Telescope, there must have been also predecessors, which basically monitored the stars in the center of the galaxy for a long, long time. And then from this one calculated back about the movement of the stars and that there must be this common center of gravity, which must have around 4 million solar masses. So if you take this, if you want to see this video again, please stop this video and click on the one given to you. Then you see the stars in the center of our galaxy whooshing around, and occasionally you see that the ones that come very close get very fast accelerated and slow quickly down again. In general, since this course is now coming to an end, module, what I can recommend you is take a look from the ESO, European Southern Observatory, the website. The same is true from the ESA. They have loads of fascinating videos, so you can just skip around. And I'm pretty sure you can fill there. If you're feeling bored, that you can easily fill there quite some time. Of course, I see that usually you would spend the time learning from morning 8 till evening 8, and then maybe socialize a bit. Oh, I heard that such people exist. So we know about this supermassive black hole. And now, well, the last thing for this lecture, before we end basically the journey to galaxies, and next week we will come back home to our solar system. Make a stop here, go quickly through our solar system. Why it is the way it is. At least as far as I understand it, and try to transport my knowledge over to you. And then the very last lecture, we go to exoplanets, planets around other suns or other stars. But here, well, on the journey home, hopefully Andromeda Nebula doesn't fall on your head. So if you remember this goal, warriors, asteroids, obelix, the only thing they were afraid of is that the sky will fall on their head. So, and this picture here, this is very interesting. This is taken from this website here. This is probably the most, or the picture of the Andromeda galaxy with the highest resolution. If you would do the full resolution, you would need about 300, 400 of these massive flat screen TVs, and then put this picture on. So next to each other, make a big, how to say, a big wall of them, and then put this picture on. You can find here the original files with super high resolution, and you can then zoom into. And with this, thank you for your interest about galaxies, and see you Monday in the tutorial session. Okay, see you then. Bye.